Good morning, or whatever it is, wherever you are. Alright, so I got most of the things for defining these curves converted to continuous form with a thing to evaluate it at a certain number of positions. So I was kind of thinking that, for instance, scaled should almost reverse its argument order. Although the 2-point thing is a little weird. I also had a bunch of other curves. Scaled probably isn't right. This is more like a blend based on a curve. Okay, so wiggle flow, I think, is... We've got a bunch of old examples with it. The function itself should be done. Arc flow, similar. Which then means arc... So as it stands, we still need that. So I had a thing that arc factor for blah of blah. That's just stage divided by stages. So that would be arc factor of 3 of stage divided by stages. Ooh. Get length of up value stages. Maybe it's not, it's probably not an array, it's just a number of stages. Okay, that seems reasonable behavior there. Only place we called that. Manual flow shows up in all of this sort of archival stuff. Manual flow weights would have been used by that same thing. So actually, arc factor. That gives me an array between those things, which is not the same as the factor. So I'd have to have a thing that was just the curve we were using for that, in order to have that thing automatically go back to our weights. I mean, that might give me a way to sort of reverse that formula. Don't know if it quite does. I might have to make some assumptions about the structure of it in order to reverse it. That's something to think about later, I think. Manual flow edges is going to go because that went. And then we have, yeah. We've got a lot of pick-by functions that are still hanging around. Bootstrap is still a specific thing. Yeah, the current flow is all those factors, so that's an alternate there. This I don't think is used. Flow stage equals stage. That was probably for doing something like Bootstrap. These functions... Oh. Right. So that is still used in a few places. Do I even need a function for that? Or do we just do function... Function of x returning a. So that would be eval flow stages function of x return and then your slowest speed. Maybe I should have a constant just as a shorthand for that. Because I do have to kind of read a function there. Visor flow. I'm using factors to just distinguish things that, oh, it's not really a flow anymore. Constant of c, return function of x, return c, and end. I was looking at wiggle range. Uh-oh. Okay, that looks reasonably like what we were getting before. And one of the things I wanted to start playing around with was the visor. That needs to be refactored. This was, yeah, it's not currently called anywhere. I was trying to use it in a similar way to my manual flow. Stage to stages, but we're getting a t factor that's exactly x. And then saving it. So arguably, this should become, well, keep that around just in case. So there is no flow, there is, oh, this was calculating meter. Right, 310, yeah. return function of x and function of t. All right, so where is my curve graph? Visor factor, so it was 0, it was 3, 10, 10, 10 before. Well, just for something similar to that. Nope, unexpected symbol, 966. Oh, right, no equal sign, just returning it. One 197. Missing a parenthesis. So that was that. 1195. Oh, also have to add that back into the, I don't know. I want to say DOM because of JavaScript. I might need to do some lookup on Bezier curves because it seemed I may have like sort of built in some assumptions about the control points. Is a no cars. Oh, maybe because this is a one-dimensional curve that I'm essentially doing. What you normally get with these is in two-dimensional drawing is that you have two-dimensional points and you essentially do it for each. What is the definition? Linear distinct points. Oh, distinct points, simply a straight line. T0 plus t of the difference, or t times the difference, equivalent to linear interpolation. I think quadratic is what we've got. No, cubic, because it is 4 points. Arrives at P3 coming from the direction of P2. Going towards P1, arrives at P3 coming from the direction of P2. These points are only there to provide additional directional information. Explicit formula of the curve. Okay, so the 3 is just part of that formula. Contain a cusp. Cubic by identical to a quadratic one. Copying the endpoints by two middle control points along line segments. So what is this? It's got different degrees of... Yellow circles. Middle control point. At the various points at which these control points are placed. So like the yellow points give us this curve. And this point gives us the purple curve. And this thing gives us that. Boom, boom, boom. Flat. So this is still a two-dimensional curve, so you can move it around here. But I'm only doing a single dimension. I would need a polynomial curve with more points to get the kind of things I want to do. B of t, sum of j equals 0 to n of t to the j, what's c? Where c is quite the little number. What the heck is n? This could be practical, can be computed prior to many evaluations, may lack numeric stability. So, looking up, maybe spline formula would be more efficient. Any linear combination. Defined by recursion. 0, non-zero. This isn't particularly helpful. Give instead of not. Piecewise constant of 1 to 0, indicating which knot span. X goes from ti to ti plus k. 0 to 1, 1 to 0. Control points, and it's, well, we'll try to explain first derivative. Not vector. Zero, zero. Or is it just 0 and 0? 0. I mean, that's 1, 1. Yes, that's a not vector and control points. Zero, zero, 1, 0, 0. And its first derivative. Right, because that's probably angle. So increasing, decreasing, and increasing. Zero, 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 1, 2, 3, 3, 3. That's 5. That would only be 4 as pairs. Linear combination of B-splines. Values of x where the pieces of polynomial meet are known as knots. Sorted into non-decreasing order. And the knots are distinct. Coincident. Up to a scaling factor, a unique spline satisfying. Ti, t plus n. So is that outside the range? Oh, because this is from 0 to 3. And that's from 0 to 3. I'm thinking I might be able to just, well, do it sort of like, okay, so we're done with you. You sort of glue Beiser curves together rotating through the control points. Are you exactly that plus 2? No, you're that plus 3 points. bk plus 1 times bk. X minus ti. I guess the ti is what's not... because they have not labeled their axes here. We've got a 0 to 3 and a 1 to negative 1. But how does that relate to x and t? Or I, for that matter? So this is a slightly stretched version of that one. Just a little bit longer with a smoother gradient in between. And it looks awfully similar to this. So that's saying negative, 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 negative 1, 2, 2, 2, 2, 2. And control point 0, 0, 0, 6. So that's negative 2 to 2. So this thing is over the not range. That's moving towards here, but we kind of move quickly through that range. And this has a much smoother derivative. It's not clear how the knots relate to the control points. Control points control polygon and marked component curves. Yeah, so this feels like sort of like an assemblage of visor splines. I want to see the data for this one, actually. Admittedly, it's a two-dimensional curve, whereas those are kind of one-dimensional curves. Combinations of spline functions as linear combinations of B-splines with a set of control points. Places where pieces meet are known as knots. Values of x where the pieces of polynomial meter are known as knots. So t is in the knots. To a scaling factor, a unique spline satisfying 0 if it's outside of the range, non-zero otherwise. Comes 1. Okay, yeah. Just if we allow it to vary continuously. B of x B of n, B of 1 is either 1 or 0, depending if it's in range. So so the knots are T0. What's the control points then? Combination of flexible bands passes through the number of points that are called control points and creates smooth curves. Degree n minus 1. 1 plus n locations called Tj, called knots, are breakpoints. Only in the range between the first and last of these knots and is 0 elsewhere. Separated by the same distance from its predecessor. That's a specific subset of uniform. Non-zero is a polynomial of degree n minus 1. The knots, when all knots belong to the same B-spline, are distinct. Uniquely defined by its knots. It's a single B-spline already extends over 1 plus n knots. Internal knots need to be extended with n minus 1 endpoints on each side to give full support to the first and last B-spline. So this is 1, 2, 3 splines with 1, 2, 3, 4, 5, 6 points. So these points seem to be coincident with the end of the spline, whereas these are not necessarily intersecting. As the endpoints do not matter, usually the first and last internal knot is just repeated. Right, so this is 0, 0, 0, 0, 5, 5, 5, 5, 5. Linear combination of splines. In order following scheme illustrates how each piece of order n is a linear combination of the pieces of order n to its left. I1, 0, I minus 1, 1. I1, I2. X squared divided by 2. X0 to 1, X1 to 2, X2 to 3. Uniform B-splines of order 3. Oh, piecewise composite Beiser curve. Last point coincides with the starting point. This is kind of what I was thinking, I guess. Loses local control. Dependent on each other. Whole spline needs to be reevaluated. They lose the interpolation property of a piecewise Beiser. Ct of some real parameter t are each spline functions with a common set of knot values. Basis functions. The weights. These points are commonly known as control points. Control point, control polygon. Yeah, maybe what I was thinking of was the piecewise Beiser. Which is something you could actually imagine calculating. Using 4 curves. Okay, cubic Beiser. Composite by composed to quadratic Beiser curves. I mean, this looks... And what's weird is that the endpoints seem to be kind of defined by 3 points, but then in the middle we've kind of got this, it's like it's not hitting this. Control points, control polygon, and marked component curves. It'd be nice if we had the data for this. Spool spline from a linear combination of B-splines. So they're only saying B-splines of order 1. Higher order B-splines are defined by recursion. Value of x are known as knots. Where the pieces of meat are known as knots. The knot vector has a bunch of repeated stuff on it. Maybe the knot vector is to take care of some boundary conditions at the end, so it just resolves down to a single point. So the stuff of interest is not including those final points. Looks like we have a curve from 0 to 0 to 0 to 0 to 0 to 0 to 0, 0 to 0. Then we have a curve from 0 to 1, from 1 to 2, from 2 to 3, and then 3 to 3, 3 to 3 to finish it out. How does that line up? That's 5. That's 8. So between 1 and 2, it's 1. That's sort of right, but it's also rising here. Before we get to 1 and 2. So that would be thought of as like the control point up here-ish. Defining this. Oop. And then from 0 to 1, one to 2, 0 to 1. We have this 1 up here and also a 0. Means we have to use this other 0. Maybe that's kind of what this stuff it does. 0, 0, 0, 1. It's definitely not clear how to implement this. I mean, there's a function, but this is saying x minus t. T is the control points. The values of x meet are known as knots, or they meet. Knot sequence 0, 1, 2 of order 1 are 0, 1. For ti and ti plus 1. But it's 0, 1, 2, spinning either side. It's 1 if it is between the 2 points. And equal to, so we would have some stuff that was there. Bi right, so it's the sum of the functions, and the functions are 0 when they're not in range. Non-zero otherwise. So that's of 1. Spline of order n of order 1, second number, degree n minus 1 in a variable x. Values of x where they meet are the knots. Unique spline satisfying. But what is the non-zero? Scaling factor becomes fixed. Conditional strength, the sum of equals 1. So this is the weighting function for which spline, but they don't really define. Well, no, they say that for order 1, it's 1, 0. And for higher order functions, x minus ti, well, that is, okay, the amount it's into that, ti plus k. Oh, so ti plus k is the order. So the order is how many control points are being used. So the amount that x is into ti the value of the knot vector out to that order the difference in the value of the knot vector. So for 2, then that's times 0 or 1, depending if you're in that range right now. And then I plus k plus 1 minus x. ti plus 2 plus 1 minus x divided by I plus k plus 1 minus ti plus 1 basis of I plus 1. So quadratic must imply the n. And that's a cubic B-spline. So does that necessarily determine the number of points? But that's BO for any I. And it's the sum over I when you do the sum. So that's each individual curve. So where do the control points come in? Is this just the weighting function that's used over those? This is sum over BI, so how do we get well, okay, so there's plus order. So you're 1, 2, 3, 4, 5. So quadratic is plus 3. 1, 2, 3. Cubic. The cubic B-spline had 4 control points. It's a quadratic. What says 6 is actually involved? Although the first region where we see anything is going to be 2 to negative 1. So maybe that's going over this. That's cubic, so maybe it means 4. BI. I is of n. No. Variable x. The n minus 1 of a variable x. Devoted as not. I'm not sure what you iterate over and how it would work. To I, what is I? B of I, combination of flexible bands. Piecewise polynomial function. Variable x. It is defined 1 plus n locations called knots. Seems like we have a lot more knots than 1 plus n. Only in the range between the first and last of these knots and is 0 elsewhere. By the same distance, uniform, where it is non-zero, degree n minus 1, continuous function of the knots. Belonging to its derivatives are also continuous. Internal knots and endpoints. Next domain is interested. Internal knots need to be extended n-1 endpoints on each side. The first and last B-spline to affect the internal knot intervals. Just repeated. Spline of nt of x is sum of I is alpha I the control point times the weight? I'm working on trying to define curves. So I want something like this, but I want it like a little bit wider maybe. And I still have to apply some adjustments to this, but it's a baseline. So I'm trying to get something that kind of gives a good, like a warm-up, cool-down kind of thing without being just, what I originally had was just like line up, across, down. But then that tended, when you put some variation on it, tended to like bounce between like the same 2 or 3 points over the course of it. So I want some slope. And I'm trying to figure out how you mathematically describe something with a little bit more detail to it. But the programming language is Lua. And I'm just trying to figure out, which is, I don't know. It's targeted for an embedded usage, so they embedded it in StepMania. But it's based on tables, which depending if you sort of leave the keys or the arrays sparse, you can have dictionaries, sets, and arrays by kind of just leaving out one of those things. It does support higher order functions, which is kind of what I'm doing now to sort of fake some currying. So all these return functions of x or something similar so that I can use them somewhat interchangeably after supplying the parameters. Yeah. Well, I think what I may have done in the past is actually sum of Beiser curves. We just kind of rotate over the points. So I've got a basic 4-point Beiser curve. I could maybe do something that took 5 and gave me 2 curves, splitting over some number of points. It would have to be a very explicit function to do that. And I thought B-splines might be kind of that thing. Yeah, that would be. But I was, one of my goals for these projects is to try and learn something every now and then. So I'm just trying to. This is not described in a implementation friendly manner. I mean, it looks kind of like what they're doing is you sort of swap between curves, but it might be a more continuous way of doing it. Piecewise constant 1 or 0. Well, a straight up one-dimensional Beiser curve probably is similar to that. I mean, we could probably get something interesting if we mixed it up a little bit. Yeah, so that's actually a little bit more like the other curve I was using, which had a little bit of a slow. It's actually sort of surprisingly not very different, but I could get a little bit of shaping it that way. And then sort of blending between those points might get something. So we could imagine the effect this would have if it was only the first half of the curve, if we did it like that. There it sort of ramps up, and then we flip that around. I imagine, if that's still ramping, could we actually overshoot that? Okay, that does overshoot. My graph is auto-scaling. So that's not exactly what we want. You probably could do this just by sticking together. Well, I don't know if you could do that. Some Beiser curves. They might not be continuous, depending on how it glued together. So I could have a thing that took 5 parameters and made 2 Beiser curves out of it, and at 0.5 each, which I mean might be useful as a sort of little experiment. Which would return a function of t that would be if did this need a then? It would be of P0, P1, P2, P3 at t times 2, and else it's P1, P2, P3, P4 at t minus 0.5 times 2. Oop, we made an error there. 950, or an up value P3. What was that, 960? Oh, right, I did P5 instead of P4. Don't worry, it stopped at P3. P3. Oh, how about we return it? Might be helpful. Yeah, so you could extend that method to give you a little bit more of a hump, and maybe if you give it a little bit more shape, something like that. Oh, now see, this is the problem I was thinking of earlier, where they're not necessarily continuous. So we have to be a little bit more careful about how I do that. So maybe this feels sort of like what the B-splines are doing. I'm just not completely sure how to translate this into code. Piecewise constant, which knot span it is. Ramps from 0 to 1 as x goes from t to ti plus k. There's 0 outside of those respective ranges. It's a triangular function that is 0 below x equals t, ramps to 1, and x to ti plus 1 and back to 0 and beyond at x goes. Because these have local support, are typically computed by algorithms that do not need to evaluate basis functions where they are 0. Yeah. Each piece of order n is a linear combination of the pieces of B-spline of order n to its left. The knots at 0, 1, 2, 3 at x equals 1, b1 equals b2 equals 0.5. And then derivatives. Derivatives. There, for evaluating spline curves in B-spline form. Comparatively lower stability. Sum of B-splines functions, potentially vector valued constants. Okay, so now we actually have, okay, yes. This is the B-spline itself is a weighting function for the control points. So for each control point, you get the value of that, which is 0 outside of some appropriate range. And now we're using p instead of n. Connected piecewise polynomial functions. 3p over grid of knots. We use 0-based indices and following. Uses O of p squared plus O of p operations. Ooh, so this is not a simple thing to execute. It's a different notation. in with n equals p plus 1. The algorithm directly, instead it evaluates S through a equivalent recursion formula. New control points. di0 equals ci. I equals k minus p dr d0 k minus p to k. That's k. Oh, that's di0 for r equals 1. dir. What's alpha? Oh, there's alpha. 1 minus air di minus 1 r minus 1 di0 equals c. K minus p. What was k? Tm. Index k, the not interval that contains the position. Whip up an x to the n equation. Well, yeah, I was playing around with some of that, and I'm currently basing some stuff on this, which is a modified form of, I'm forgetting which probability distribution function. So we've got x to the a minus 1 times 1 minus x to the a, which for its defined range, which is only 0 to 1, gives you this, and then I have some fudge factors that kind of make it approximately 0 to 1, which is a combination of, and I've actually removed some, there's like a curve adjustment parameter on one of these. It's a combination of that, and I spent some time like looking through mathematical curves to see if there was something that would define what I wanted. And I didn't really see anything. So you can kind of see how this combines. And then that kind of affects the centering of it a little bit. It's a little bit different in each direction, but so that's something. But I mean, like this form has too gentle of a ramp. So I kind of want something, and I was playing around with this, kind of like reversing this curve and having that do both sides, but that basically gave you just, well, that if I wasn't experimenting with the double form right now. You were saying x to the n, where, I mean, n is just that apparently. And actually, this is x to the a minus 1, which is kind of similar. Only in a finite domain and 0 elsewhere. N minus 1 humps either upward or downward. Oh, do you mean more like... for some multiplier? Okay. Which doesn't seem to be doing a whole lot right now. I mean, maybe we need to do, like... some ups and downs. I almost had something interesting there. Anyway. Ah. Yeah, you might be able to flip that around. Well, one of the things I would, well, I guess that could be a slightly smooth variation of the manual flow. But I kind of wanted to throw maybe some variation in there. So to flip that around, is that +1? Yeah, that's +1. And then we need to flip this entire thing. And no, 2x and 2 of x plus 1 minus 1. No. So that would be kind of a smooth version of the... And then even factors of that would kind of give us more or less... which is not necessarily a super easy thing to adjust, but I could have a couple of settings for it. So that could be an alternation to the manual flow. Might give me a little bit more variation as we bridge into this. All right, so double biser, I don't think is currently very useful. So manual flow factor, this is a exponential factor of a power, and then it returns a function of x. Which, so I guess that this is, we could rewrite this as 1 minus. Do we have... Okay, we do have that kind of exponentiation here. So we have x minus 0.5 times 2. And just to be sure, and that is our return. Exponential factor of 4. This is sort of the shape. I was hoping to maybe have some room to make that asymmetric. But is that something we could put in to test out? So that's effectively this. So scaled exponential factor of 4, and that's this thing. One of the reasons I'm redoing curves, I'd kind of like to improve this setup a bit. And that might affect these as well, but our basic, that should be able to, and that could actually run into some limits there. And then we've just got a very long cycle wiggle there. 3, 4, 4, 3, 7, 3. This spends more time at the top, so I might want to tweak down some of the difficulty setting stuff. Although we're getting some pretty big swings, but they have a lot of other things in this algorithm I probably need to work on. It kind of got complicated trying to put all the constraints I wanted on it. So I'm still trying to understand how this thing works, even if I don't end up using it. That's a recursive definition. The algorithm. The new control points. What was k? That's what I was trying to figure out up here. Index k, define the not interval that contains the position x equals k, k plus 1. The not interval. So k minus pk. Finds it contains positive x, xk to k plus 1. K plus 1. This is so many points back to k. Oh, no. Of R0 for that many points prior is equal to the control point. And then IR DI equals C. DI equals CI for I equals K minus P. I equals K minus P to K, interval that contains the not interval, so that's in not space. But this is saying there's a CI for I equals K minus P. Contains the position. So do we simply not evaluate the, like these? You've got, since these are, that's math stuff. Since these have no space between them, do we never have an x in this range for those? It has to go here. So then I equals K minus P for this would put us back this many values in the support vector, or in the key vector. No, because that's still a negative number. No. Right. So we go out to here before we get a range that works. Go back to there to get I. And then you have CI. And these never exist. So you just have to sort of skip over the... I'm not sure how it works mathematically to talk about ranges that don't exist, but... So we look at places where there's an actual range. We go back to get the corresponding I. Does not compute the B-spline directly until it evaluates SS with an equivalent recursion formula. The iterations are complete. We have SXS equals DKP is the desired result. Which are guaranteed to be multiplied by 0. Now, for the implementation on a computer, it requires memory for P plus 1 to P2 plus 1, P plus 1, P plus 2, temporary control points dir. Exactly written once and read twice, but reversing the iteration over I, counting down instead of up, Memory only p plus 1 temporary control points. By letting dir, we use the memory for dir minus 1. So we can reuse the memory as well. Zero-based index for temporary control points. dj equals cj. The previous index is I equals j plus k minus p. Cj for 0 to p, iterate for r equals 1 to p. J must be counted down. One minus alpha j, which is defined below, times d of j minus 1. J must be counted down. But j depends on j minus 1. So is this just stack space? Here we go, calculate that, store it, and then use it above. Why must it be counted down if we need minus 1 in our calculation? Wait. dj equals dj? J equals p to r? How do you define dj in terms of dj? After the iterations are complete. Does that mean dj in the previous iteration? Evaluates s of x, kxtcp, index of not interval that contains x. So that's calculated outside of this. This is just to evaluate at x. Array of not positions need to be padded as described above. But you've already done the not checking separately. Array of control point, degree of B-spline. D is initially the control points according to certain values. Yeah, okay, so they're iterating, double iteration, d of j equals, so r, with, okay, so this was the d of 0 thing, where equals control point. For r of 1 to p plus 1, j counting down Right, and then you can do the counting down version because it uses you can have access to the previous iterations values of D on both ends. And R comes into it somewhere in the alpha calculation. 1 to p plus 1, which t of minus r. Look, it's going through all the control points and adding their influence somehow, but using the partial result. One minus alpha alpha. And those are the t's. So telling you how much to weight each of those points. So I sort of understand what's happening. And it's sort of similar to what I was doing with the multi-part Bizer. Bize, however it's pronounced. But this one is better set up to do the smoothing effect. I think it probably would be a effectively linear. So we could try transcoding that. And then probably, yeah, and then I think I would have to do some digging into how you make composite Bizer curves work. Because I'd swear I'd done that before. All right, so we've got... So this is... So I'll probably end up with a relatively constant thing. Shoot, did we have... literal array syntax? I don't think I've had much occasion to use it if we do. This might be 5.1. Expressions. Table constructors. Maybe you don't have literal arrays. Because they're really tables. There are things to operate. I think sugar for a name. Yeah, I don't see any easy way to define an array of things. Is there any evidence of that? Or maybe it's just a table that has unnamed values. Okay. So that's actually constructed with this. Okay, empty table. Yeah, I don't think I ever did an array of numbers anywhere. That's named. The other thing is that this is a zero-based algorithm, so we might have to be careful with that. So I could probably simplify this for my purposes. So this was all defined to be zero-based. And this only does the index of not interval that contains x. Hmm. The other problem is, I'm kind of looking at time and wondering if I want to get into this right now. Because this is direct, or rather it's a direct implementation, but it could also be pretty gnarly. Well, I think we do have something we can try out. And then we tried putting in the exponential factor for our weighting. And that's still a little bit whip. So we are testing. B-splines. Yep. No. There we go. How much do we do today? Oh, we want to switch that back for actual play. We did a fair bit of cleanup. And we got our exponential curve. And we need to turn off the graph for now. We should have a pretty well-tuned model, though. So I'm still using the one probability distribution function for some of the limits. Might be impacting some things. And we can see a little bit of the same leveling going on. Yeah, I might turn down the top a little bit because this one spends more time at the top than the other algorithm did. Because 57 and 59 are going to be probably pretty hard for me. Neither of those are actual, so maybe it's just wrong, but it's often wrong in the other direction too. All right, clean up. Rewrote that. New function. Rewrote that. Rewrote that. Notes. Clean up. So that's kind of another work in progress thing. But since it does take like 45 minutes an hour and I want to have lunch at some point, I would like to switch over to actually playing this game. So all the coding, mathy curve stuff is over. If you're here for that, thanks for dropping by. If you still want to hang out, I'm going to be back in a few minutes to play StepMania. We might keep this selection, or maybe I'll have to bump some stuff. I'm going to drop the stream briefly and change settings. So I've got this optimized for resolution right now, whereas I want a little bit higher frame rate for that. So meanwhile, thanks for hosting, and thanks for watching. I'm not going to host anything there, because I'm going to be back in a bit. I am normally coding in the morning and then doing some StepMania sometime around now. I'm switching over Monday, Wednesday, Friday. But yeah, if you want to hang out, I'll be back in a moment, and bye.